So more on variation, more on direct variation. But now the relation is not going to be linear, but it's going to be nonlinear. Remember, last time we looked at linear direct variation. As the number of liters go up, the depth of the water increases in a linear way. This is described by a formula for y in terms of x, where x is multiplied by a constant, which we call the constant of proportionality, to give y. It looks a lot like the equation of a straight line, where c, the y-intercept, is 0, because these all start in the origin. And we've looked at lines on a graph before that were not straight, where a straight line is defined by y equals a constant times x, or at least one that goes through the origin, is described by this formula. Non-straight lines are these are examples of non-straight lines. If you were to plot y equals x squared, or y equals the square root of x, or y equals x cubed, those lines would all not be straight, remember? So these are all examples of direct variation where the relation is non-linear. So if you were told that y is directly proportional to x squared, that's how you write that information. Your formula for y in terms of x would look like this. So y would equal the square root of x multiplied by a constant. Once again, k, the constant of proportionality, right? If we were to plot a graph like that, a line like that, it would look something like that. Okay, if you were told that y is directly proportional to the square root of x, the formula for y in terms of x would be y equals the square root of x multiplied by a constant, a number. Once again, your graph would look, if you were to plot this and you had an actual number for the constant, your graph would look something like that, which is not a straight line. That's what we're getting at. That's why it's called nonlinear. If you were told y is directly proportional to x cubed, then your formula for y in terms of x would, of course, be y equals x cubed multiplied by a constant. Right? This constant could be 1. It could also be 70,000. Right? Let's do an example problem. What if you were told that y is directly proportional to x plus 1 squared? That's this type, right? Y is directly proportional to x squared. This is a lot like it, except it is now proportional to x plus 1 squared, which really comes down to basically the same thing, except if we were to write this statement using our directly proportional symbol, we would say y is directly proportional to x plus 1 squared, right? So we put that directly in there. And we're told that when y equals 32, x equals 3. Okay, first question is find the formula of y in terms of x. So using this information and this information, we find the formula for y in terms of x. Well, y is directly proportional to x plus 1 squared, so I'm going to write x plus 1 squared multiplied by a constant, right? this is the shape that our formula is going to have. All we need to find now is what the constant of proportionality is in this case. And we can figure this out because they gave us one of the points, one of the coordinates of the line, one of the combinations of x and y values. That is true in this equation. So we plug those numbers in and solve for k. So when y equals 32, x is 3, so we plug in 3 for x squared. Okay, so 32 equals k times what? 4 squared. 4 squared is 16. K times 16 equals 32, so we divide both sides by 16. 32 divided by 16 is 2, so 2 equals k. So we found the k value. That wasn't the question though, it said find the formula. So we rewrite this with the correct constant. Y equals 2 times x plus 1 squared. Now we have a formula that we can use to make a table of values, plot the coordinates, draw a line. This formula describes the entire relationship between x and y. We can use this to draw a graph and to find any other points on the graph, which is what we're going to do here, because they want us to find the value of y when x is 2. Well, that's going to be easy because we have the formula to find any combination of points, any combination of values for x and y. So we plug in x equals 2, right? Y equals 2 times, when x equals 2, so 2 plus 1 would be 3 squared. So y equals 2 times 3 squared is 9. So y equals 18. That is our answer there. So that's an example of a direct variation that is nonlinear and that is built up with an x squared. Yeah, and examples with the square root of x or x cubed would, you know, basically be the same thing. Let me do a real life example of a nonlinear direct variation. This is a pendulum. So it's a piece of rope, rope, whatever, could be whatever. It's stuck here. This is like a cannonball or something, and we swing it, right? It swings this direction and it swings back. We call that, the time that takes, we call that the period of the pendulum. How long does it take for the cannonball to go this direction and come back? There's an actual formula for that, which says t, the period it takes in seconds, how long it takes for it to swing there and back, is equal to, it's around 2, the constant of proportionality in this equation is around 2 times the square root of the length of the pendulum, so this piece of rope or whatever. This is the equation that physicists have found is true for the period of a pendulum. So really, and that's, I've always thought this was really cool. It doesn't matter how heavy the pendulum is, how heavy the cannonball is. It doesn't matter how high you start swinging it. The time it takes for it to swing and swing back is only dependent on the length of this rope, which is fascinating, I think. So this is a real life direct variation that is nonlinear, and that is the time period in seconds is directly proportional to the square root of the length of the pendulum. And like we could say, what if the length of the pendulum is, so when L, the length of the pendulum is 4 meters, how long will the period it takes to swing there and back, how long will it be? Well, all we do is plug in our length into the formula. T equals 2 times the square root of the length of the pendulum, which is 4 in meters. The square root of 4 is 2. 2 times 2 is 4. So the period of this pendulum would be 4 seconds if this length of the string is 4 meters. Pretty cool. So we actually use this in real life. Anyway, have fun doing some practice on this.